We will continue today with the DTL technology. Up to now, we have seen how to implement the inverter with this technology. And first, the transfer function, and then we obtain the transfer function, and then we looked at how to find the fan out for output low case and output high case, and then we determined the power consumption here in the last maybe couple of minutes. Now we will look at how to implement. Other type of gates, like how can we make a NAND gate here. This is maybe a very simple addition of another diode will allow us to make a NAND gate. Here is showing the implementation. So just by maybe adding this block here, we obtain a NAND gate. Okay, so why is the NAND gate? We can just apply voltages here, and then talk about this. Maybe I'm going to add one more column here for simplicity. Okay, so let's say this is Vx voltage. What is that voltage? So if VA can be put as 0.0 volt or 0.2 volt. Let's say that we apply here 0 volts. That means voltage-wise, a low voltage. Okay, so VB, we can apply low voltage also. So if both of the voltages are low, Vx is going to be 0.7 volt. Why? Both diodes are going to be on. So diode A1 will be on, the other one will be on. So if this is the case, Vx is 0.7, then these two junctions cannot turn on. So this junction and then this junction cannot turn on. Therefore, Qn is off. And Qn is off means V out is going to be VCC. So V out is going to be VCC, that means output is high. So therefore, the state of the output is going to be obtained here. The transistor states, we can also, we could draw them here. So it's not that easy to write it here. The states, maybe I'm going to erase this and then say what is Qn, maybe here, and then here I'm going to add maybe two more things here, DA1, DA2, and then dB. Maybe I should do this Qn and dB, because they are, they go in parallel. So for the first case, both of them are on. This is on, this is on. And then V out is this. Why? Because Qn and dB are both off. Okay. So if we apply here low, 0, and then if we apply here 5 volt or VCC, that means we apply low and high. What is the voltage here? Vx. So Vx, if one of the inputs is low, 0, this is going to be again 0.7. So this will be still 0.7 volts. And one of them is going to be on. DA1 is going to be, let's say, on. But then this one is going to be off. DA2. Why? Because VB is VCC. So this node is set to 0.7 by this 0 voltage. And then this is VCC. And this is going to be DA2 is off. Okay. So therefore, even for this case, the output, I mean, the devices are going to be both off, and output is going to be VCC, which is high voltage. Okay. So if the other way around, we apply here 0 and then 0.7 here. So sorry. I made a mistake. If this voltage is 0 and this voltage is VCC, then this is high, this is low. Then the same thing happens here. This voltage now is set to 0.7 volt. Now this one is off, this one is on. And then here they are both off, and then output is still VCC, which is high. Okay, so if both of the inputs are VCC, okay, so then this is high, this is high. Okay, then both of the diodes are going to be off. Okay, so this will be off, this will be off, and the voltage at Vx is going to be, in fact, 1.5 volts. Why? Because Qn will be sat and the other one is going to be on. So this is going to be 0.8, this is going to be 0.7 volts, therefore that's going to be 1.5 volts. So what is going to be output? Since the transistor is in saturation, it's going to be 0.2 volt and output is going to be low. So logic wise, if you look at this logic, this is a NAND circuit, okay? 2-input NAND. Okay, so very simple, just by adding one extra diode, that's achieved. So if we want to make a NOR gate, NOR gate is a little bit maybe more complicated, but if you look at also last year's exam questions, you can find about that value or the way that it is implemented. You know, the devices are in, you know, has to be coming in parallel. So maybe, you know, we can look at again in literature or last year's exam questions about 2-input NOR gate. Okay, please check how to implement 2-input NOR gate. Okay, so you know, maybe there are some extra things here. We say that we can make an inverter or a NAND gate here, but there is a problem here. We didn't talk about that problem up to now, so probably you are not aware of it. The problem is, you know, once this transistor goes into saturation, and then we want to switch it back to off, it takes some time. You know, so let's say we have an inverter here, and then input goes from high, you know, it goes high to low, okay, Vin. So this used to be VCC, and then it goes to 0 volts, okay. So when this happens, you know, initially the diode here would be off, but then it goes to on, okay. This diode used to be on, and it goes to off. And then this transistor, initially, it used to be SAT, then it needs to go to off, okay? So, in order for this diode or the transistor to go from SAT to off, this diode here, base emitter junction, needs to be discharged. So it used to be 0.8 volts, and then, you know, that 0.8 volts, the charge in base emitter junction, you know, it is deep in turn on, the charge in base emitter junction needs to be discharged so that QN can turn to off, okay. So in the previous circuits, we don't have a path for this capacitance to be discharged. So you can assume that, you know, there's already, you know, that diode, the diode here is, you know, that the PN junction, but that is saturated. So it is as if you have a capacitive path here, 0.8 volt, and then you are trying to discharge this. So how is this going to be discharged? The current cannot go towards here. So it takes very long time. So it is not practical to turn off this one easily. So that's why, you know, this circuit, typically we add a resistor here to the base of the transistor to discharge that that base charges. So either, you know, that RE or R base, not okay, we don't call it R base, RE, is one side is connected to this, or VE can be maybe 0 volt, you know, 0 volt, or even less voltage than 0. So we apply a voltage there, or ground, you know, we connect that. So therefore, this resistor path is going to be, you know, used for discharging. So SAT to off is therefore a critical thing for discharging, okay? So and this way, when this voltage goes from high to low, output therefore is going to go from high, you know, it's going to be turned off. So output here is going to be going from low to high, okay? But, you know, this time going high, V out, going to VCC, this will be, in fact, will be, maybe that time is not going to be that sharp. So this response maybe will take like a time like this, or it will take time like this, or even longer, okay? So, one reason why this is going to take time is maybe the load capacitance, C load, if there's any, okay? But let's forget about this. Even if this is not here, this base charge needs to be discharged, okay? Base emitter junction needs to be discharged. So by putting here an RE, this is going to be shortened, okay? RE edit to switch that fast. So therefore this is something that we need to pay attention. VEE can be either 0 or VEE can be, I don't know. If you want to use another supply voltage to make it faster, you can make it like, maybe 0.5 volt, more so, 0.5 volt, or something, okay? Of course, this will be affecting our fan out, because even in normal operation, there's going to be a leakage through here. Therefore, keeping the transistor in SAT is going to be a little bit more difficult. Because remember, for SAT, we were saying that beta I base should be larger than IC. Note that RE decreases fan out and max because what? Why? Because we know that beta I base should be larger than IC. Okay, so this I base is reduced as some current IRB current goes to RE. Okay, so just as a note here, you can look at it. There are some variations here. Okay. Any questions? Now, in fact, we do one more thing here. The DTL, we normally use this modified version of the DTL. The DTL, performance can be improved by adding some elements. Let's just find the fan out equation here. The fan out equation is, we calculated this before. This is the fan out equation, okay? This is how we determine the fan out. Now, if you look at this equation, we calculated this before. We say that here, the current I base, this is I base, times beta F should be larger than IC, which is this current IC. And this IC has two components. One of them is this here, but the other one is this one here. And this other component is coming from next. And then interestingly here, that also current I in prime, this is I in prime, also is related with RB. So RB is happening both here and here. Okay, RBX is RB because it's coming from the next stage. Okay, next stage. Okay, so therefore, if we change RB to increase fan out, it will not be really improving that much, because the current coming from the next stage also depends on RB. So this is just to remind you the equation. This is fixed, so we don't want to do anything with this, but here the fan out really depends on that RB. And the smaller it is, IB is increasing, but also this is also increasing. So considering this, the circuit is really modified to this one. So now, that's diode. We already have the diode in there, right? So some designers thought that, there's already a diode here, and there are two diodes, right? So typically, in order to implement diode in the IC technology, you just don't do the diode itself, because BJT is made. So that's what you do. This is diode connected. Diode connected BJT. Okay, that's how you implement the diodes typically in a CMOS in BJT technology, in a bipolar process. So some people thought that, they said, let's just split this, RB resistance, and then design it like this. So add a Q1 here. So that RB, so rho value is something between 0 and 1. So if you do this, you will notice that here the fan out is going to be much better. Why is it going to be much better? Now, in order to explain why it is much better, maybe I can draw you this next stage here. The next stage, maybe I should do that. Okay, so the next stage is going to be something like this. Okay, it's coming from the next stage, the current. Okay, let me prevent confusion. Okay, so here there's a resistor, another resistor. Okay, so this one, it says here, and then one more diode. Okay, so so the fan out was limited for the output low case. So the output low case is this one, low, okay? So when does this happen? This is in saturation. When this is in saturation, okay, I just draw similar next gate, okay? So there will be maybe one more of this thing, and then one more of this thing, and one. But you know, I'm interested in this I in prime current. So when this is SAT, output low case, the V out is going to be 0.2 volts. So if this is 0.2 volt, this is going to be on, and then this voltage is going to be 0.9 volts. So if this voltage is 0.9 volts, this will be off. So if this is off, then this is VCC, and these two resistors now is going to be RB. Okay, so nothing changed in that stage. And then you know, if you want to calculate the fan out is going to be, you know, the current here, this is IC, right? I mean, we say that it's going to be IC beta F times I base of N should be larger than IC or IRC plus N times I in prime. Okay, so this side is the same, and then it's going to be VCC minus 0.2 volt divided by RC plus N times VCC minus 0.9 volts divided by RB. So it's same. Okay, basically here we have RB, and then it's a large resistance. We can select it to be large, and therefore this current I in prime is going to be small. Oops. Okay. Anyways, so this is VCC. But the improvement comes from the other side. This is enlarged. Okay, why is it enlarged? So let me put the beta F here, and then write that IB or IBN. I can write maybe first here, another place. So again, this case occurs when this is output is 0.2. That means when input is 5 volt. Okay, so if we apply 5 volt here, which is VCC, this one is going to be off, and then the diode is going to be on. This is SAT because we select the resistance values properly so that it's going to be SAT. So what about Q1? We know that this junction is on. Okay. So and then there's going to be current in this direction, and that current is going to be subtracted to RE, so IB. So this current is going to be IRE. Okay, so this current, let's call it I emitter of 1. Okay, so what is the state of Q1? So what is this junction? We know that this junction is going to be on, so it's going to be either 0.7 or 0.8. But what about this junction? Now, you know, if there is an IE current in this direction, some of that current will come from here, and this is off, so it should be coming from here. That means there is a positive voltage here. So that means this junction should be off. Why? Because positive voltage here. So if there's positive voltage here, then that's going to be off. So if this junction is on, and then the base emitter is on, and then base collector is off, collector, emitter, base. Therefore, this transistor should be in forward active. Okay, Q1. So maybe I can take a note here. Base emitter 1 is on, but base collector of 1 is off. Therefore, Q1 is in forward active. Okay. So why are we doing all these? The purpose here is to find I base and then say that the I base is larger. Now here, you know, in order to find the voltage equation here and find the current IE, that's what we need so that we can find I base, IE1. Here, you know, if you look at the circuit here, this current due to loop, you know, if you have the loop here, this current is also IE1. Okay. So what about this current here? What about this current? You know, that's the base current. Transistor is forward active. So that current is equal to IE1 divided by beta plus 1. Okay. So that's very small current, basically. So so therefore that voltage either can be neglected or you can include that in the value. So this positive voltage is small. Okay. So from here, then IE1 can be calculated very easily because VCC is going to be equal to IE1 plus rho RB plus, I mean, we can write this thing, but we can ignore it later on. RB times IE1 divided by beta plus 1. Okay, can be neglected. Plus 0.7 volts coming from Q1. Okay, plus 0.7 volt from dB. This is from Q1, and then plus plus 0.8 volts. Okay, so here we can be ignored. And then from here we can determine IE1. Okay, if IE1 is determined, then IE1 minus RE is going to give us I base. Okay, so I base of N can be calculated, and that I base of N can be written here. Sorry. I base of N. Okay, so maybe I should do this. This one is carried here. Okay. That's how we can find the fan out. So the interesting thing here is that rho RB times IE1. Sorry, I made a mistake here. This should be multiplied by. Right? I mean, in order to find this voltage, IE1 times rho RB. That's the voltage. So in any case, if you do this, as you see here, this one will be related with 1 over rho RB instead of just rho RB. Okay, this is proportional to rho RB. So since rho is less than 1, we will have much current here. Therefore, fan out is going to be decreased. So here it is RB, and this node, this is RB, but here it's related with 1 over rho RB. Why? Because rho RB is going to be coming in order to find IE. Rho RB is going to be, coming to the other side. Okay, so I guess we have an exam or question for you, take-home exam, to solve this and then find this thing yourself. But this is really the EE312. I mean, the initial one was for you to warm up, and then this one is a more real device, modified one. And this could be removed, dB, but we added in there so that we can shift the breakpoint to 1.4 volt instead of 1.7. Okay, so I hope this is clear. The fan out is limited by output low case, are not equal to each other. Solution, maybe add extra diodes. Okay, maybe in modified DTL, input, the input low is equal to 1.4 volt. Instead of 0.7 volts. I mean, if you look at it, you will be seeing this. So therefore, noise margin low is going to be 1.4 volt minus 0.2 volt, which is 1.2 volt. So switching time can be solution is add a discharge path. Okay, is that clear? Okay. next, we will see the TTL circuit, and I'm just going to start to this, maybe explain the idea, and maybe voltage transfer function, but just the idea maybe. You know, today we'll be doing 1 hour course. You know, why do we prefer TTL? Actually, if you go to, you know, market today, you cannot really find DTL circuits, but still, I'm sure you can find TTL gates coming from maybe early times. But TTL was much more popular for BJT-based gates. And, you know, I guess, you know, one person, you know, said, looked at this, you know, two diodes back to back, two diodes. Oh my God, this is transistor. You know, instead of drawing two diodes back to back, if you draw this circuit, then you also have two diodes back to back. Okay, so this is the idea initially maybe, and then later on we see that this has many advantages also by doing this. So this this is how you can implement a gate. Okay, so you know, we claim that this is a way to implement an inverter. Okay, this is called basic TTL. In fact, in the future, we'll be adding some more elements here. But first, you know, we need to start by understanding this. You know, why this is going to be acting like an inverter. Okay, and in order to understand this, we will look at the extreme cases first, and then we will be obtaining voltage transfer function. So let's first look at this by itself. You know, what happens if the input is, let's say, 0 volts. Okay. If the input is 0 volts, I'm going to write this thing with this color. So what is the state of QI? So there's this junction and then this junction, right? So this base emitter junction is going to be on. Why? Because there's a current path here. So there's a path here that current can pass. So if that is on, okay, so base emitter of QI is on. So QI can be either SAT or forward active. So can it be forward active? Forward active means, you know, we need to have a current in this direction. But you know that due to QO base current cannot be negative because the transistor doesn't allow it. Therefore, you know, that current, this IC of I is going to be 0. If that is the case, then beta F times I base of I is going to be larger than IC of I, which is equal to 0. So therefore QI, so QI should be in saturation. Okay, so if so, I can calculate also beta F I base of E, sorry, I base of I, which is equal to IRB, can be easily calculated to be 5 minus 0.8 divided by RB. Okay, and then since ICI is equal to 0, that means it's equal to IB of O, which is equal to 0. Then QO is off. If QO is off, V out is VCC. Okay, so we started here with 0, and then output is VCC. So it is an inverter. Is that okay?
Yes.
Okay. So one extreme we already determined. The other extreme is this case. Let's draw it again. Maybe here with the green. I'm going to do it here. This maybe it's better to draw it again. Oops, sorry. Okay, now we will apply the other extreme here, 5 volt or VCC. So we expect the output to be low. Okay, so this transistor needs to be in SAT. So here we can look at again this junction and check, you know, if this junction can be turned on. So this should be off, right? Base emitter of QI should be off. When Vin is equal to 5 volts. I mean, that junction cannot turn on. So if that's the case, then QI can be in two different conditions. QI is either going to be off or reverse active. Which one? So notice that there is this diode here. Okay. So is there a current path here?
Yes.
If yes, then that junction should be on. Okay. So this base to collector base collector of QI is on. So it cannot be off. The transistor should be in reverse active. So if it is in reverse active, we can find the currents. What is the current value? The value of the currents, but you know, QO, there is going to be I base of O will appear. Okay, and if we select the RB and RC values properly, then QO will be in SAT. If QO is in SAT, then V out is going to be equal to 0.2 volts. So we started with 5 volts as the input, output is 0.2 volt. So this is an inverter. Okay, so I mean we have an inverter. Okay, is that clear? So input is 0. Input is 0. QI is SAT. Okay. So this is in SAT. And if that is in SAT, QO is off. Therefore, output is VCC. If the input is 5 volts, QI is reverse active. And then this is going to be reverse active. And this is going to be in SAT. And therefore, output is going to be 0.2 volts. Is it okay? So this is the therefore TTL circuits. So we determined already the extremes in this graph. Input 0, we said output is going to be VCC. Input is 5 volts. Output is going to be 0.2. For input 5 volts. Okay, so we know that. So what about the transition? Like, when this is going to be happening, that transition? I guess we better maybe talked about it later on. If it is okay, maybe I can just talk about the first transition point. So if this was 0, this transistor was in SAT, and then this voltage here is how much? I need an answer from you.
0.2.
0.2 volts. Okay, so if this is 0.2 volts, that's not enough to turn on this. So QN is off. Okay. So if we increase this voltage to 0.4 volts, this node is going to be how much? 0.6. So still it's going to be off. Okay. However, when we get here 0.5 volts, this node is going to be 0.7 volts. So QN starts turning on. When it starts turning on, remember the order. We go from off to forward active and then to SAT. And then SAT to forward active and to off. So turning on means it goes to forward active. So if it's becoming forward active, output is going to be decreasing. So we obtained the first breaking point. So this is going to be V input low, and that value is equal to how much?
0.5.
0.5. Yes. Thank you. Okay. So what happens if I apply here? Now I solved this almost. I said I won't, but I'm tempted. So if we apply here 0.6 volts, then if this is still in saturation, this is going to be 0.8 volts. QN goes to SAT. So this goes to SAT very quickly. So this voltage is going to be 0.5 volts, 6 volts. So we will call this thing V input high, and then output will remain at 0.2 volts. Okay. So, somewhere around here, transistor goes into reverse active. QI goes to reverse active somewhere here. So if you want to find that value, you will be confused because of the model. The model, remember, reverse active to SAT switching is not a good thing. I mean, in our models, we say it is SAT to reverse active, and this region is complicated. And then, but we can say that, what about this current? You know, how can it be SAT? That's ICI. That ICI is going to be negative here for that value. ICI can be negative. You know, in fact, in the real transistor model, remember this was coming like this, and then it was going like this. So here, ICI could be negative. Okay, so that current is going to be enough to put QN to saturation, and that's how real function. Okay, so we obtained the simple voltage transfer function here. We will analyze this a little bit more next time. I don't want to stop here, and you will be soon getting an you know, take-home exam or something like that about modified DTL and this basic TTL. But we will be seeing this basic TTL more next time, like, you know, what happens in the voltage transfer characteristic, maybe fan out, we'll be finding those. Okay. Any questions? Did we start the recording? I guess we did.
Evet hocam, recording gözüküyor.
Okay. Good.